Alright, so let's get into our question. Our question, I'm going to summarize this, is the first part. It wants us to correlate the specific heat at constant pressure and the specific heat at constant volume for an ideal gas to be related by a shift in the gas constant R. And we could kind of see that right here, but what we're going to do is that I'm going to derive this equation from this graph right here. And for part B, I'm going to briefly explain why specific heat at constant volume gives the change in thermal energy. But let's start with part A first. With part A, we can see that the distance when you hold pressure constant and volume constant, they are equal to each other, which tells us that the change in thermal energy at B and change in thermal energy at A, which is these two parts right here, when you hold one or the other constant, they're going to be equal to each other. And for them to calculate the change in E thermal, we can use the first law of thermodynamics, which is that is going to be equal to the work on the gas plus the heat energy. Remember, this is the work on the gas specifically. I know this is kind of hard to read because it's really tiny. My apologies. As for to calculate A, we can use this, put it, and we know the work is 0 because at A, the volume is being held constant, and when volume is held constant, there's no work being done on the system. Now we're just going to be left with the heat energy variable at constant volume, but we know by the textbook that that is going to equal to the number of moles multiplied by the specific heat at constant volume multiplied by the change in temperature, and that's just what we're going to have since the work is 0. But for the second part, we're going to have this plus the work, because there's going to be actual work done in the system, because now pressure is going to be held constant, and so now we have Q at constant pressure. This is going to be the same as this right here. The textbook tells us as well, but the main difference is that instead of specific heat at constant volume, it's specific heat at constant pressure. And this extra part right here, Professor Tornado helped us with that. It's the work is the area under the curve, and that's just the volume, changed volume, multiplied by the pressure. And the reason why it is negative is because work is being done on the gas and the pressure is moving outwards. So when we equal those two parts to each other, like this part right here and this part, we will get this equation. And I've repeated that equation right here. And the problem here is that we need this to be in terms of t, so we can cancel out some variables to get it to look very similar to this equation right here. And we can do that by relating the ideal gas law. And when you take the change variable in, and well, you do that, right? When you do that, you can move it into the equation, and you'll just be left with the pressure multiplied by the change in volume is equal to the number of moles times the gas constant times the change in temperature. And we see that this is the same as this, but don't forget the negative. So when we plug in or substitute it in, we get this equation right here. And now we can see that each variable has an n and a change in t variable. And we can cancel those out, and we'll just get left with this. And when we move the variables around, we'll get left with an equation that's very similar to the first equation that we have. And we can see that the specific heat at constant pressure is equal to the specific heat at constant volume shifted by the gas constant. So now that that's done, we're going to quickly move over the explanation for why specific heat at a constant volume gives a change in thermal energy. This was a little hard for me to understand a little bit, and it was kind of confusing based on the textbook, but I did watch a video that helped me understand it a lot more, and I'll link it down so you guys can watch it as well. Basically what this person is telling us is that when heat is moving into a closed system with a constant volume, that is the heat capacity, and that we're trying to figure out how much the temperature is going up or down. And that's very similar to one with the ideal gas laws. When you hold volume constant, when pressure goes up or pressure goes down, the temperature will change with it. So that can be quantified into this equation right here, which is the specific heat at constant volume is equal to the heat energy at constant volume over the number of moles multiplied by the change in temperature. And when you move these variables around, we can get this equation right here, which is can be used for any ideal gas process. And that is how we can identify a change in thermal energy when there's constant volume for specific heat.